Hello everyone, I am Pragya Srivastava. I am here to record a lecture on control systems. The course code is KEC602 and presently in my lecture we are discussing its unit 2, which is time response analysis. Previously we have studied what is time response analysis when we are studying the response of a system with variations in time. That is called time response. What happens when time is changing to the response of a system? So before heading into second order systems, we have obviously studied first order system. We are going to solve some basic numericals based on time response. So in this system, in this numerical, we see that there is a electrical network where it is a series circuit consisting of a resistance R and an inductance L. It is connected to a supply of voltage Vt. We have to find an expression for current in S domain. So we have to take the Laplace. Okay. Now we have to calculate the value of current when t is equals to 0.5 milliseconds with the value of resistance being 1 into 10 raised to the power 3 ohm, that is 1 kilo ohm. Inductance is 25 millihenry and the supply voltage be 50 volts. We have to neglect initial conditions. Now, so we see that this is an electrical network where we can very well apply KVL. So the input Vt will be equal to the drop across this resistor and the drop across this inductor. So drop across resistor will be I into R and the drop across inductor will be L di by dt. Now when we take Laplace, we have to convert it into Vs will be equal to I of S into R. So this is the first derivative, so we take it SIS into L. Now we can take this IS common, so IS will be IS into R plus SL will be equal to Vs. So now we have to see that from here itself the input to output relation can also be figured out. So presently let's calculate IS. In this numerical we need to calculate the value of current at t equals to 0.5 milliseconds. So from the previous relation we have IS is equals to Vs upon R plus SL. What we are actually trying to do is we have the value of resistance as this, inductance as this, and voltage Vs like 50 by S. How we are doing this? It is a step voltage. So step voltage means we are actually considering a step signal. So for unit step signal, the value of A is 1. So here we have not A. The value of A is 50. So for unit step signal, generally we have ut as equal to 1 by S. So here we'll be having it as 50 by S because A is here 1 and here A is 50. So it is a step voltage. Now Vs is equals to 50 by S. Substituting these values, we get Is is equals to 50 by S into the value of R, that is 1 kilo ohm, plus S times 25 millihenry. Then we can find out it is by simplifying we have 2000 upon S into S plus 4 into 10 raised to the power 4. We are doing this partial fraction method to find out the coefficients of first and second term. So we have got the value of A as 0.05 and B as minus 0.05. So this is the resultant value of current. Again we have to take the inverse Laplace. Now inverse Laplace, we have 0.05 is equals to 0.05 into 1 minus e raised to the power minus 4 into 10 raised to the power 4t. So this term goes as coefficient of exponential term. Now we have to substitute this value of t as 0.5 millisecond, or it is 0.5 into 10 raised to the power minus 3 second. So we are substituting the value of t, and here IET will be equal to 0.05 into 1 into e raised to the power minus 4 into 10 raised to the power 4 into, this is the value of t, 0.5 into 10 raised to the power minus 3. So this is the actual value of current. So this is how we solve the numerical. Considering the another numerical where we have a system has unit step response. Unit step response means RS will be equal to 1 by S. Okay, and we can call it that US was just 1. So it is unit step response. Determine the impulse response and ramp response. So first of all, we have to determine impulse response and ramp response. So what we have actually, when we are talking about response CS, it means we have the value of, let's understand the structure of the question. We have CT, it means we have CS2, just we have to take the Laplace, so it means we have CS. So when we have CS, and also we have the value of RS, okay, so we have the value of CS, we have the value of RS. Now we can have the ratio of two of them, we can have the ratio of two of them. Now what we are actually doing, this CS is composed of the response when RS was 1 by S. Now of course we have to see the impact on output when the input becomes impulse, problem number 1. Secondary, when the input becomes ramp, problem number 2. So this is all we are supposed to do. So let's take it step by step. We have declared that the input is unit step, so RS is 1 by S. Taking Laplace of this CT value, we are having CS is equals to 1 by S from here, and then e raised to the power minus 0.1 t, which gives out the second term, 1 upon S plus 0.1. So here is the value of overall transfer output. Now we are trying to find out the transfer function. Transfer function will be CS by RS. CS by RS, CS is this thing, RS is this thing. You just divide the two of them. So when CS is this, RS from here we have is this. Now this is the overall system, transfer function of the system. This is the overall transfer function. Now we see that this is the transfer function. For this transfer function, for this particular result, for this transfer function, see very well we can see that the transfer function is CS by RS. Now we have this transfer function, okay. We also have the value of RS. So RS means you have to find out two cases, one for impulse, another for ramp. So you have to find out CS for impulse input and then CS for ramp input. So once you multiply this transfer function with impulse input, you will get the impulse response. Another second case, you multiply the transfer function with ramp input, you will get the ramp response. So this is the two things we have to do. So here impulse response is RS. So for this, it means for the first case, you have to multiply transfer function will be equal to CS into RS, which is 1. So this is transfer function will be, one more, just I'll erase everything on this slide. So here I can see that response will be equal to transfer function into RS. So this is the transfer function. So for the first case, the transfer function is for RS is 1. So you are multiplying TF into 1. Here we are multiplying just 1 here. So multiplying 1 will give me this Laplace, inverse Laplace of this, which is 0.1 e raised to the power minus 0.1 t. So this is very well impulse response. In the case 2, we have to multiply it with ramp input. So ramp input will be nothing but t. So for t, we have to multiply it by s square. So here, instead of multiplying by s, we will multiply by 1 upon s square. So here we see multiplying by 1 upon s square. We can find the values of a, b and c using partial fraction. And then a is 1, b is minus 10, c is 10. So here is the value, and then we take inverse Laplace. For this term we will get t. For this term we will get, for this term we will get t. For this term we will get just 1, and then for this term we will get e raised to the power 0.1 t. So this is the required kind of a question which we have generally from the from the time response analysis. From here and onwards, we are going to start second order control system. So we have to study response of second order system. Now, for first order system, like in my previous lecture, for first order system, we have studied all 4 inputs. I'm repeating it again and again because we want these things on our tips. So the first one was impulse, the second was step, the third was ramp, and fourth was parabolic. So we have studied the response for all 4 cases. Now, this was for first order. For second order system, we will be at this level of study, we will be studying only the step response, because only studying the step response will give me the behavior of second order system in all the respects. So we are not studying the response of second order system for impulse, ramp and parabolic. We are studying only for step. Now we will study when it comes to the response in time domain. It means we are talking about CT. So we have to study certain parameters. What are those parameters? The name of those parameters or time domain parameters are delay. What is the delay? What is the rise time? What is the peak time? What is the overshoot? What is the settling time? And then we have to study, of course, the numerical problems based on these things. Of course, there will be a mathematical model. There will be a mathematical model based on delay of second order system. There will be a mathematical equation based on rise time, peak, overshoot and settling time. So of course we have to study the mathematical models for all these of them, and then we also have to study before this the response for a second order system subjected to step input. So step input, when we are giving the step input, the response is called step response. Response of second order system. Now from here I can start it as, let us imagine that the characteristic equation of a second order system is s square plus 2 zeta omega n s plus omega n square. So from here and onwards we have to study what is characteristic equation. Now characteristic equation is nothing but, let me write, transfer function will be let's say of a negative feedback system, gs upon 1 plus gs hs. So characteristic equation means the denominator equated to 0. The denominator equated to 0 is nothing but the characteristic equation. So from here, let us study more upon these variables. So this is the coefficient, this is again the coefficient. Now we are able to see zeta. Sometimes in some book it is represented by this symbol also. So it is zeta, another is n. So this is nothing but frequency, and from this omega n we have certain other frequencies. This is damped frequency, this is undamped natural frequency, and then in the previous lecture we have studied what is damping actually, and zeta is called damping ratio. Okay, and both of these terms, natural frequency and damped frequency, are related to frequency of oscillation. So these are the description of certain terms which we have in the characteristic equation. So the characteristic equation consists of s square 2 zeta omega n s. So the second term is 2 zeta omega n. So it is twice of damping ratio into undamped natural frequency. Next is which is equal to 0. Okay, so when we try to find out the values of s, and of course we have to follow the formula to find out the roots of second order equation, then using the formula, Srivatava's formula, we get the values as minus 2 zeta omega n plus minus root over 2 zeta omega n square minus 4 omega n square by 2. So this is what we call as the roots of characteristic equation, that is s is equals to minus zeta omega n plus minus omega n root over zeta square minus 1. So let us consider the different values of damping ratio. So for different values of damping ratio, the value of s, so this is of course s1 and s2. Why am I calling it s1 and s2? Because these are the two roots, and of course we have two roots here based on this plus minus sign. So one goes with minus sign, minus zeta omega n minus omega n root over zeta square minus 1. Another is with plus sign, minus zeta omega n plus omega n root over zeta square minus 1. So here we will substitute the values of zeta, and for different values of zeta we will study that what happens to s. Now this s is nothing but roots of characteristic equation, and also they are the location of poles for the concerned system. So let us substitute zeta as 0. When zeta becomes 0, the two terms are imaginary when zeta is 0. What happens is this term reduces to 0, and from here we have a negative value within the root over. So from here we can see that we will be having the value as plus minus j omega n. So these are the imaginary values. So we can write it like this. And this is also a case where we get the roots on the where the system is marginally stable. Next we have two roots are real and equal when zeta equals to 1. So when zeta equals to 1, this term reduces to 0, and then we have the two roots. So this was the first case. Second case, we have two roots at minus omega n. So here we have one more root. Let's make it with different color. So at the same point, which is omega n, we have two roots. So let this be omega n, let this be omega n, and this is sigma and this is j omega. The two roots are real but not equal when zeta is greater than 1. So let's say zeta is greater than 1. So considering the value of zeta to be like let's say this zeta square is 10. Let's say zeta square is 10. So here from the values of zeta having more than 1, zeta square is 10 minus 1 is 9. So root over 9 is 3. So 3 omega n. So of course this is a real value. So 3 omega n, when you add with this omega n, it becomes another value. When you subtract, it becomes some other value. So we will be having real roots, but those two roots will be unequal. Now let us consider the value of zeta between 0 and 1. So 0 and 1, it means this value will have the overall value of root over will be negative. So of course we will have some j value from here, and then this is the real term, this will be the imaginary term. So real plus imaginary, it means the s will have a pair of complex conjugate roots. So from here we have analyzed the characteristic equation of second order control system, and we will study more on this in my next lecture. Thank you.